There are different kinds of solutions, but all of them are going to be homogeneous mixtures. Now, homogeneous, this is uniform throughout. The different kinds of solutions would be gaseous solutions. Gaseous solution would be like air. Air is a solution of nitrogen and oxygen and some other gases. It's a homogeneous mixture. Air is. We could have liquid solutions. Those are the most common ones that we deal with, like salt solutions, sugar solutions, etc. And then we have solid solutions. Solid solutions would be like alloys, brass, stainless steel. There are many different compositions of brass, and there are many different compositions of steel. Even aluminum, this is most likely an aluminum alloy rather than pure aluminum. This aluminum alloy, they add some other elements to the mixture to get some desirable properties. You have gaseous, liquid, and solid solutions. In solutions, the particles are dispersed uniformly throughout. Therefore, they're homogeneous. These last two bullet points are not that important. This is different than a suspension. A suspension is like muddy water. It might look homogeneous initially, but the mud will settle to the bottom. It doesn't have to be as big of particles as mud. It has to be silky water with smaller particles. Eventually the particles get so small that they stay suspended indefinitely. That's a solution. Solutions, we have two major components of solutions would be the solute, what's dissolved, and the solvent, major component, liquid. Solute and solvent. Solute is generally defined as the minor component, solvent usually defined as the major component. The identities and roles can reverse depending on how you do it. And so solute's a minor component. So in this particular case, we're going to make a mixture of water plus copper 2 chloride. Copper 2 chloride is going to be the minor component, water is going to be the major component. So this is our solvent. Normally water is a great solvent. Water is a great solvent, it's polar. Water has some interesting properties. It can dissolve a lot of salts. Unlike other liquids that aren't as polar, they have a hard time dissolving any salts. And those dissolved salts are important for lots of chemistry. And so the solute, copper 2 chloride, we dissolve that and we form a solution. The solution is going to be a homogeneous mixture of copper. It's actually going to be copper 2 ions and chloride ions. Now the copper 2 chloride lattice is very strong. This has a very high melting point. And so how can water do this? How water does this is there are collisions. Collisions with the surface, they knock the ions off. If the ions get knocked off the surface, then they can get encapsulated by water molecules. Now, if we have a 2+ ion here, the negative end of the water will surround itself. If we have a minus ion, then the positive end of the water molecules will surround the ion. This creates what's called a solvation sphere or hydration sphere. The solvation spheres and hydration spheres are stabilized by intermolecular attractions. The intermolecular attraction here would be what's called an ion dipole attraction. The full ion charge of 2+ being attracted to the dipole of water. The dipole of water will have a negative end, which is the oxygen, and a positive end, which is the hydrogens. So the ion dipole attraction, like this, helps stabilize the ions in solution. Otherwise, it'd be very difficult to break this lattice apart. We wouldn't want to dissolve, but in this case, it does dissolve. Like that. Solute and solvent. There's some more vocabulary associated with solutions. For example, concentrated and dilute. Concentrated just means there's a lot, relatively large quantity of solute. Dilute is small. So this is showing a couple of things. This is showing a chemical reaction. So, for example, copper metal. Does copper metal dissolve in water? No. The only way to get it to dissolve is to attack it, the copper, chemically. And so they're attacking it with an oxidizer, in this case, silver nitrate. What's doing the oxidizing here? Is it the silver or the nitrate doing the oxidizing? you would expect the nitrate to be doing the oxidizing because when we look at the chart, nitrate is a more powerful oxidizer than silver. So silver is a decent oxidizer too. It's pretty good. You know, silver stains everything black because it oxidizes everything and precipitates out silver metal. So silver is not a bad oxidizer either because silver metal is quite stable. However, nitrate's better. If nitrate does the oxidizing, then we expect bubbles of NO gas to form. These bubbles of NO gas will be colorless initially, and then eventually those bubbles will turn what color? Orange. This gives a beautiful orange smoke, they say, characteristic of nitrate being the oxidizer. So when we look at this and examine the copper, this is a spiral of copper wire, there are no bubbles. You know what those are? Those are crystals. And when we look closer, those are crystals of silver metal. So nitrate's not doing the oxidizing here. So anyway, whatever theory we have regarding this has to match experimental fact. You know, fact trumps theory. You know, the theory could be wrong, but the fact is fact. The fact is, this is silver metal. And there are no bubbles of gas. In fact, there's no orange layer of gas above this, like a smog layer. And that's what it is. You'll see the NO2, the oxides of nitrogen. When you go for automobile smog test, you know, they look for NOx, you know, oxides of nitrogen, create that brown smoke. Now, anyway, going back to this, there is no brown smoke. In fact, silver is doing the oxidizing here, not nitrate. And so was the ordering wrong, or are we missing something? Why isn't nitrate the oxidizer? Why is silver the oxidizer?
Silver is the oxidizer because it's trying to take electrons away from the copper to create a solid.
Yeah, but nitrate would too. You know, each silver ion takes 1 electron, each nitrate takes 3 electrons. Nitrate would take electrons as well.
But there's no gas forming.
Yeah, which says that nitrate's not taking the electrons. If nitrate were taking electrons, then there would be gas forming. There's no gas forming. So why isn't nitrate taking electrons? It's a more powerful oxidizer, is the question.
Is it electron rich?
Nitrate's electron poor. Nitrate's electron poor. In fact, you know, based on this, nitrate's more electron poor than silver ions. It's not because of the positive charge, it's just because of its ranking. In fact, there is no positive, it's a negative charge there. So why isn't the nitrate doing the oxidizing? What's that?
Because of the H plus.
Because of the H plus, yeah. There's not enough H plus to make this happen, you know. If we add acid to it, then it would happen. We're missing key ingredient. So this is like what we said, you know, earlier. If you have 1 cup of, let's say this is 1 cup of sugar, 4 cups of flour. 1 cup of sugar, 4 cups of flour, you can bake something, right? But can you bake anything with just 1 cup of sugar? No flour? What if there's some? What if somebody spilled some pieces of flour on the countertop? Could you use those and bake a cake? No. We need significant quantities of acid for this. It's not going to happen. And in this particular reaction, when we look at this particular reaction, yeah, nitrate should do the oxidizing, but there's no significant quantities of H plus. We need acid to do this. This is just copper with silver nitrate. If it were copper with silver nitrate with acid, like HCl or acetic acid or any acid, then yeah, nitrate would be doing the oxidizing. If we just need to pour some acid in here, and then it would work. But there is none. It turns out there's a minuscule amount of H plus in water. Do you know how much H plus there is in water? 10 to the minus. What's the pH of water? The pH stands for the power of 7. So it's 10 to the minus 7 molar. It's too little. Too little, not enough. So it's not going to do it. And so what's going to happen is the silver ions will continue to attack the copper. When silver attacks the copper, it takes the electrons and precipitates out silver metal. The copper, in turn, gets oxidized to copper 2. And the copper 2 ions go into solution. This is what's causing the blue color. The blue color is going to darken. And so this would be pretty dilute. This would be much more concentrated. It has a much deeper blue color. And look how much silver is precipitated. Do you see these things hanging here? Those are silver crystals. Silver crystals form these little branch-like patterns. It's called dendritic crystals. So they form dendrites when they grow big. So anyway, this is just to show two things, the redox chemistry and concentrated versus dilute. Okay, well, how much more concentrated can it get? You know, it's just going to get a deeper and deeper blue color. Is there a limit to how much copper can go into this? In fact, this is going to be copper 2 nitrate. Is there a limit? In other words, is copper 2 infinitely soluble, or is there a limit? And so that comes up. This brings up our next set of terms, and that is solubility. Solubility is used in two ways. There are two definitions for solubility. One is qualitative. Qualitative, like for example, chlorides, bromides, and iodides are all soluble except for silver, lead, mercury. Nitrates, acetates, chlorates are all soluble. So those are qualitative. But the other definition is there is a limit. For many things, there is a limit. You can't dissolve an infinite amount. What is that limit? Well, that limit we call the solubility. So, for example, what is the solubility of sodium chloride? Two ways you can answer that. One, it's soluble in water. Chlorides are soluble in water except silver, lead, and mercury. So sodium chloride will be soluble in water. Or two, well, if it's soluble, how much will dissolve? So typically what's done to measure how much dissolves is you take 100 milliliters of water and then dump in as much sodium chloride as possible and get as much to dissolve. So if you take 100 milliliters of water, it turns out only 36 grams of sodium chloride will dissolve. If you tried to dissolve one more gram, let's say I have 36 grams, if you try to dissolve one more gram and make it 37, it won't. It won't dissolve. It's already full. It's reached its solubility. Solubility is how much solute will dissolve in a given amount of solvent. And that given amount is typically 100 mils at a given temperature. When we dissolve 36 grams of salt in 100 milliliters of water, we call it saturated. Saturated means you can't dissolve anymore. It's reached its limit. If we have less than 36 grams, it's called unsaturated. That means there's room for more sodium chloride to dissolve. And so we want to pay attention to these terms. Solubility, saturated solution, and unsaturated solution. These are in the slides. You can get the slides on. Yeah. Let's look at these miscible and immiscible. Do you know what miscible means? Well, it's soluble, but that's not good enough for definition.
Can easily be taken apart.
It's
Broken down.
well, I used the term before. I used it when I was talking about methanol in water. Does anybody? Methanol and water, or water and water. I asked you, how much water can I dissolve in water? How much water can you dissolve in water? Infinite, right? Mixing water, I can, I have a little bit of water here. If I have 100 milliliters of water, how many milliliters of water can I add to it and mix? Actually, more than 100. Infinite. I could add as much water to water as I want because it's just going to give me water. Water plus water gives me more water. And so there's no limit, right? Methanol is the same thing. How much methanol can I add to water? Infinite. Methanol is so similar to water, I can add an infinite amount of methanol to water. Pretty soon, though, I have more methanol than water. And then the solvent-solute roles are reversed. That is, methanol becomes the solvent and water becomes the solute. But anyway, that's miscible. Miscible means infinitely soluble. And so it dissolves in all proportions. There's no limit. Immiscible means not soluble at all. They don't mix. So zero solubility. And so some things don't have a limit. Those things that don't have a limit are called miscible. A supersaturated solution is when we have more solute than should be allowed. How does a supersaturated solution form? Well, what happens with supersaturated solutions is they're formed under one set of conditions and move to another set of conditions. This is the classic supersaturated solution. This is sodium acetate. Yeah, it's probably easier to see. But So basically what they did was they heated this up. We got hot water. With hot water, you can dissolve more than in cold water. Like hot coffee, you can dissolve more sugar in hot coffee than in cold coffee. So what they did was they heat this up and then dissolve it to saturate it with sodium acetate. And then they cool it down. They cool it down slowly. If they cool it down slowly enough, what happens is it cools back down to room temperature. When it cools back down to room temperature, what should happen is all the excess solute in here should crystallize or precipitate out. It doesn't. Do you know why? It doesn't because it has a hard time crystallizing. Do you see those crystals? So what's happening is we have a supersaturated solution here, and then do you see what they're going to do? They drop this tiny crystal in. You know what this tiny crystal is called? It's this crystal of sodium acetate. It's called a seed crystal. It's a seed crystal. The reason it needs a seed crystal is because of the crystal structure of sodium acetate. What is the shape of acetate? Sodium ions are just round, but what are acetate ions shaped like? Acetate ions are going to be shaped like this. You know, this can be a CH3 and a COO minus. There's one more resonance form for this with the double bonds over here. But this would be the acetate. This molecule, part of the molecule, what shape is that? Tetrahedral, and this would be trigonal planar. So what this is kind of like, it's kind of like a ball, a sphere, and then this triangular thing on the end. This triangular thing on the end is flat. And so it kind of has a weird shape to it. when we look at sodium acetate, the crystal acetate crystal lattice. When we look at the crystal lattice of sodium acetate, you can see this kind of the shape to this. You know, this kind of round end, and then actually they aren't showing the whole thing here. But it has a weird shape. And that weird shape means when we make a crystal of sodium acetate, the acetates have to be perfectly oriented in order for the crystal to grow. If the acetates are slightly tilted or at an off angle, the crystal doesn't grow. And it's because of the odd shape of the acetate ion, it makes crystallization hard. And so the purpose of the seed crystal is to provide a template for the ions to stack on it. You know, if you have a seed crystal, then the ions know where to go. Whereas if there's no seed crystal, by chance, random chance, everything has to be oriented perfectly when they coalesce and come together to start a crystal. That's called nucleation. And so it's hard to nucleate these crystals because of the shapes of the ions. Some crystals are easy to nucleate. Like if this were ammonium chloride, it's easy. Ammonium spherical, chloride spherical, it's easy. And so it's really hard to form a supersaturated ammonium chloride solution, but sodium acetate is really easy. So sodium acetate's used. And so this is supersaturated sodium acetate. It should crystallize out. And so all it needs is a little seed. There's the seed crystal. Once the seed crystal hits, then the other crystals form on top of the seed crystal. Yeah. That's to show how much, all that is excess solid. There's a huge difference in the solubility at different temperatures for sodium acetate. There's one more I want to show. There are other ways to get it to crystallize. Agitate, dust, other things. You know, if there's some dust there, then it potential for crystallization as well. You can see the crystals there starting to grow. Some people scratch the inside surface with a stir rod to get it to nucleate. Scratches in the glass can get it to nucleate as well. So the glass, in order to form a supersaturated solution, the glassware should be very smooth. So those are all excess crystals of sodium acetate. Sodium acetate forms nice crystals. And so people do this trick. They grow a pillar of sodium acetate by letting it crystallize out as they pour it. So it's not freezing there. Those are just crystals that are crystallizing out. Let's see. Diet Coke is another one. Diet Coke and Mentos here. Basically, this is another example of a supersaturated solution, but this is a gas dissolved in a liquid. Do you know what's in here? The gas that's in here, is that air? Carbon dioxide. It's not air. This is pure carbon dioxide. It's not high pressure either. It's just 1 atmosphere of pure carbon dioxide. Well, you know, if that's 1 atmosphere of pure carbon dioxide, then the partial pressure of CO2 in here is 1 atmosphere. Do you know what the partial pressure of CO2 in air is? Well, air is a very minor component. I mean, CO2 in air is a very minor component. So the partial pressure of CO2 in air is like 0.03, less than 0.03 atmospheres. And so we're going from 1 atmosphere of CO2 to 0.03 when you open that. Well, that makes a huge difference in how much CO2 gets dissolved, because the higher the pressure of the CO2, the more CO2 is forced into the liquid. And so if all of a sudden all that CO2 escapes, then there's nothing forcing it back in. What we have here is something called the dynamic equilibrium. Dynamic equilibrium is that CO2 molecules get forced in here, and CO2 molecules are coming out. It's in a state of equilibrium because the amount of CO2 is fixed and the amount of CO2 dissolved in here is fixed. It's dynamic because that never stops. But when we open this lid, then the CO2 being forced in here all of a sudden is going to go way down because there isn't nearly as much CO2. And we're no longer in this state of equilibrium. In fact, we're going to be supersaturated. Although we're supersaturated, the bubbles don't form quickly. The bubbles don't form quickly because of difficulty nucleating. And so mentos will help nucleation because on the mentos close up, there are cracks and fissures in which bubbles can nucleate. And so mentos provides a nucleation site for this. And so let's take a look at this. And so the mentos are going to act as seed crystals here. And then we get the mentos fountain. So then the bubbles rapidly nucleate and grow. Otherwise, this is the speed of nucleation and growth is pretty slow. There are other things that can do the same thing with mentos. Okay. It looks like alka-seltzer, but that's not alka-seltzer. Alka-seltzer is a chemical reaction. Generate CO2.
Are the mentos not a chemical reaction?
No. Mentos is just acting as a catalyst for helping the bubbles form. You could use other things that will get bubbles to form. You could use like potassium iodide, not that you want the potassium. Potassium iodide is more difficult to get, but that helps as well. There are other things that help bubble formation. But no, it's not a chemical reaction. Let's go back to this. Here are some examples of miscible and immiscible. This leads to a rule. Like, for example, octane and carbon tetrachloride mix in all proportions. They're very similar to each other. They're very similar in the sense that they're both nonpolar, and they both are London dispersion or instantaneous induced dipole, or induced dipole interactions only. And so, since they're very alike, like water and water, you know, how much water can you mix with water? Infinite. How much methanol can you mix with water? Infinite, because methanol and water are very similar. And if they're very similar, they mix in all proportions. However, gasoline and water are dissimilar. Gasoline's nonpolar, water is polar. Light does not dissolve light. So we have a rule for molecular compounds. And the rule for molecular compounds is like IMFs dissolve like IMFs, or like dissolves like. We have rules for ionic compounds as well. Nitrates, chlorates, acetates are soluble. Group 1 and ammonium are all soluble. That has to do with the lattice, you know, how strong that lattice is. The stronger the lattice is, the less soluble it is. And so things like group 1 and ammonium cations don't form very strong lattices, nor do chlorides, bromides, nitrates, those. But phosphates, carbonates do. Phosphate would be a -3 anion. -3 anion is going to be hard to break off. Carbonate's a -2. And so if the lattice is very strong, it's hard to dissolve. And so some lattices, salt lattices, will dissolve, some won't, depending on the ionic bond. But what happens is, let's say this is sodium chloride. What happens with sodium chloride is it does have strong bonds, but the water molecules, some of them will have enough energy to knock ions off the surface. When the ions get knocked off the surface, it forms these. What do we call these spheres? These are called hydration or solvation spheres. And what type of IMF holds the ions here, or helps stabilize the ion? What type of intermolecular forces are ion dipole attractions? Ion dipole attractions. These water molecules aren't stuck here. They can exchange back and forth, but consistently we have a sphere of water molecules surrounding that, and that's going to help stabilize it. And so it turns out that typically when we think about solution formation is called dissolving or dissolution. Dissolving and dissolution are the same thing. When we're looking at dissolving a solid like this, we break it up into 3 primary steps. One, we got to break the solute apart. That is, okay, we got to break the lattice apart. 2, we got to break the water molecules apart to make room for the solute. And so we'll separate the water molecules so we can fit an ion in there. 3, we set up the solute-solvent interaction. The solute-solvent interaction here is an ion dipole, which is fairly stable. Favorable, fairly favorable. Otherwise, it wouldn't dissolve. We got to form something decently stable to replace that lattice, which is quite stable. And so those are the steps in forming. The steps in forming a solution. When we take a solid solute and we dissolve it to form a solution like this, we got to break the lattice apart. We got to break the water molecules apart, and then we form the solute, chloride, sodium ions, solvent, the aqueous part, interactions here. Okay, this is also a dynamic equilibrium, because what's going to happen eventually is we're going to hit the solubility limit. When we hit the solubility limit, we've saturated the solution. There are no more ions that fit in here once it's become saturated. Once it's become saturated, then even if I add more salt in there, it won't dissolve because the water is saturated with ion. Now, it's going to be at equilibrium because there's going to be no net change. However, it's a dynamic equilibrium. Dynamic means what? Equilibrium means there's no change, but dynamic means there is a change. This is dynamic equilibrium because what happens is, can you stop the water molecules from colliding with the salt? Let's say it's saturated now. It's saturated, there's no more room, but can you stop the water molecules from colliding with the surface and knocking ions off? No, you can't. And so dissolution or dissolving continues to occur, but what happens at the equilibrium is that the crystallization rate, what happens is this ion comes over here and gets stuck. And so if this ion comes and collides with the surface here, if it's moving at the right speed, right direction, it could stick. If it sticks, that's called crystallization or precipitation. And so what happens when this becomes saturated is that dissolving continues. It's just matched by crystallization. So the dissolving rate is equal to the crystallization rate. So we're just going in circle, but there's no net change. That's what's happening. So this is what it looks like here in terms of these arrows. Okay, when the crystals dissolve, what do we call that? Dissolving the crystals is called? Well, it's not saturated yet. This is just, let's say, Yeah, solubility. And then as we dissolve the crystals, the dissolving process has another name. What's another name for dissolving? Dissolution. And that's what most people call it. They call it dissolution. So right now we have net dissolution. You know, we just added this is unsaturated. In fact, this is just pure water, let's say. Well, what's going to happen is as more and more of the solute dissolves, then there's a bigger probability that solute particles can strike the surface and stick. So this green arrow represents what? The black arrow is dissolution, the green arrow is precipitation or crystallization. And so the first two show net dissolution. The dissolution rate is greater than the crystallization rate. But eventually it's going to get so concentrated, it's saturated. Once it's saturated, then we know that the dissolution rate is equal to the crystallization rate, and we're just going in circles. Once we hit stage C here, this is called a dynamic, this is going in circles, equilibrium, because we're not going anywhere. Dynamic equilibrium. Now, some things are more soluble than others, than other factors, and then we can adjust the solubilities. How can we adjust solubilities? There are things that factor. So, this is something we really can't adjust the solubility for. The strength of the crystal. If the crystal solid lattice for the solute's too strong, then it's not going to be very soluble. So it's the strength of the forces. We have to look at the forces holding the solute together, the forces holding the solvent together, and the forces that hold the solute and the solvent together. In other words, we've got to look at how much energy does it cost to break apart the solute, how much energy does it cost to break apart the solvent, and how much energy do we get in return for solute-solvent interactions, that is like the ion dipole attraction I pointed out earlier. We'll look at the energetics, and that's going to tell us. So something like sodium chloride soluble, magnesium oxide is not soluble. Magnesium oxide has too strong of a lattice to work. There are other factors. The partial pressure of a solute gas. So this is like CO2 over soda water. The higher the pressure of CO2 over the soda water, the more CO2 dissolves. The temperature. The temperature impacts solids and liquids differently than gases. If we're dealing with a gas, if you have soda water, what's going to happen if you heat that Diet Coke? If you heat that Diet Coke, what's going to happen to the solubility of CO2? Does it stay the same? Or does it go flat quicker? Or does it stay carbonated longer? It goes flat quicker. So gases and heat are not good for solubility. It's like oxygen in ponds. If the pond temperature gets too high, not enough oxygen to support marine life or aquatic life. Here we could look at dissolving like ethylene glycol. Ethylene glycol is an alcohol. Alcohols are very water-like, like small alcohols like this. Ethylene glycol can mix in high proportions with water. Ethylene glycol and water are very similar. And so ethylene glycol is very soluble. I don't know if it's miscible, but it's very soluble in water. Probably miscible. Whereas oil and water, of course, don't mix. In order to get oil dissolved in water, we have to break the oil-oil attractions, we have to break the water-water attractions, and we have to form the oil-water attractions, which aren't that favorable. Whereas here, it's no problem. We can break the solute-solute, break the water-water, because what we form is something very similar. Light dissolves light. Here's gases. At lower pressures, we're going to get less gas dissolved. The pressure is going to force the gas molecules into the liquid. At higher pressures, at higher concentrations, we're going to get higher concentrations or higher solubilities. So this would be like 1 atmosphere of pure CO2. This would be a lot less than 1 atmosphere of pure CO2.
So if you had like a soda can and you shook it to get some of the CO2 to go into the air in there, and then you just left it for a while, would it go back to the same equilibrium state and it would go back into the...
It would go back, right.
Okay.
Yeah. If you shook it, and shaking it's going to cause nucleation to occur. It's going to drive out, it's causing agitation, so it's going to drive out some of the gas from the liquid. But if you let it sit long enough, then the gas will reach that state of dynamic equilibrium again. Just reestablish it'll reestablish the exact same equilibrium. But it'll take a little bit of time.
What about the water and gas?
What's that?
You mentioned mix them together, and then when you leave it, it'll separate them. Water and gasoline.
Water and gasoline? If you,
There's no way to get them to mix at all.
well, you could use an emulsifier to mix them, but emulsifier is cheating, though. It's not really mixing. You know, what emulsifying agents do is, like say you want to mix oil and water, and you want to mix it evenly. You don't want it to separate out in layers. What you can do is you can encapsulate the oil in little spheres, and these spheres, on the outside of the spheres, they have what they call hydrophilic ends, and on the inside of the spheres, they have hydrophobic ends. And so this is how soap works. Soap is like an emulsifying agent. If you look at emulsifiers, that's a cheating way of doing it, but you know, there is a way to get them to mix. These are emulsifiers. Emulsifiers are like this. You know, they have this end, which is hydrophobic, and this end doesn't like water. So this end likes oil, so the oil will be here. If you have enough emulsifying agent, what you can do is you can completely encapsulate the oil droplet. So let's say there's a droplet of oil. We completely encapsulate it with this. This end sticks into the oil, but this end likes water. So all of a sudden you have a little bubble that can move freely in water. So let's see if there's a decent picture of one. This is kind of a cartoon picture of it that's showing it how it works. So let's get emulsifier. This is kind of what it looks like. It's a drop of oil. Those can be dispersed with water. Soap works similar to this. And so then oil and water can mix. There are natural emulsifiers that are used for like mayonnaise. You know, mayonnaise is like a oil water mix. So people make natural emulsifiers from eggs. Eggs make excellent emulsifiers because they contain the fatty substance lecithin. This is lecithin. And so they give that. But without cheating, it's not going to mix. Gases become less soluble at high temperatures, but solids typically become more soluble. And so this is ammonium chloride at high temperature. So ammonium chloride at high temperature, you can dissolve a lot. So for example, let's say at 80 degrees, you can dissolve over 60 grams. But if we cool it back down to room temperature, at room temperature, then there should only be 40 grams. So there's got to be 20 grams extra. So if you take this from 80 degrees and cool it back down to room temperature, there's 20 grams too much per 100 milliliters. And that too much is going to crystallize out. In this case, ammonium chloride has no problem nucleating crystals. And so there's not a problem with supersaturation. This is immediately going to crystallize out as a precipitate. So you'll see precipitation occur as you pull this down. Most solids are more soluble. Most liquids are more soluble at higher temperature. So yeah. Right, those are some terms that are associated with solutions. Next, what we're going to look at are the composition. You know, different ways of expressing composition. One is mass ratio. You know, mass ratio would be mass of solute over total mass. Total mass would be the mass of the solution. Mass of solute over mass of solution. This is the mass ratio here. If we have a mass ratio, mass of solute for mass of solution, let's say you have 50 grams of solute over 100 grams of solution. So your mass ratio would be 50 over 100, which would be what percentage? If you had 50 over 100, it would be 50%. And so for big mass ratios, we use percent. For small mass ratios, let's say you had a mass ratio of 1 per million. If you had a mass ratio of 1 per million, then percentage isn't very convenient. We'd use part per million, or part per billion, or part per trillion, or part per thousand. For small mass ratios, use ppm, ppt. For bigger mass ratios, we use part per hundred for a percentage. And so it's the mass of component A over total mass. Total mass would be mass of solute plus mass of all the solutes plus mass of solvent. When 125 grams of a solution, so that's the total mass, 125 grams of solution, total mass, was evaporated to dryness, 42.3 grams of solute was recovered. So we have 42.3 grams of solute for every 125 grams total. And so the mass fraction would be 42.3 over 100 and 25, 42.3 over 125. So we take the mass fraction and multiply it by 100% to get the percentage. So take the mass fraction, multiply by 100%, we'll get the percentage. If we want it in parts per million, we'd multiply by a million. If we want it in parts per billion, we'd multiply by a billion. Parts per trillion, we'd multiply by a trillion. But that has to be with small mass fractions. With big mass fractions, we want to use percentage. More convenient. You are to prepare 2.50 times 10 squared, 250 grams of 7.00% by mass sodium carbonate solution. What mass in grams of sodium carbonate and what volume in milliliters of water do you use? We're going to use the density of water as 1.00 grams per milliliter. And so we have 250 grams of this solution. 250 grams of sodium carbonate solution. Mixture. And then 7.00%. So 7.00 out of 100. 7.00 what out of 100 what?
Solution.
Yeah, it's going to be 7.00 grams out of 100 grams. Now, one of those is a solution. Which one will be the solution?
7.00.
Actually, the 100 grams will be. This is the total, 100 out of 100 grams total. Well, the total is the solution. The solution is the solute, which is sodium carbonate, plus the solvent, which is water. And so this is 7.00 grams of pure sodium carbonate for every 100 grams of mixture. And so what we can do is we could just use dimensional analysis. So if I have 250 grams of sodium carbonate, then how many grams of solution is that? So
250 grams of sodium carbonate solution. That means there's 7.00 grams of pure sodium carbonate for every 100 grams of solution, sodium carbonate solution. So the sodium carbonate solution cancels and leaves you with 7.00 grams of pure sodium carbonate. So for every 100, well, I have 250, so that's
3,571.4 grams of total solution.
Well, they give us 250 grams. They just
And
total
that's
solution.
7% of it. We want 100% of it, and then minus that to get the water.
Yeah, that's what we do. But how much sodium carbonate will we need? Well, we need 7 plus 7 plus 3.5, so 17.5 grams of sodium carbonate, pure sodium carbonate. To figure out how many grams of water we have is, this 250 grams. So the grams of sodium carbonate solution, this is the mixture, is equal to the grams of sodium carbonate, pure, plus the grams of water, H2O. Since this solution, the mixture is only made up of two things, sodium carbonate and water. And so the grams of sodium carbonate solution we know is 250 grams. And the grams of sodium carbonate we just calculated, this is 17.5 grams. So 17.5 grams plus X is equal to 250. And so the grams of water, we're going to get this way. The grams of water we're going to get by subtracting. So first we'll get the grams of sodium carbonate using the composition here. That's pure sodium carbonate. Versus sodium carbonate solution. And then we'll do the subtraction. 250 minus 17.5 gives us 233 grams of water. 233 grams of water is how many milliliters? Yeah, 233 milliliters. All right, let's take a break here and then we'll start up again. Break.